Welcome to the first chem activity of Chem 121. In this chem activity, we'll address the central question, is organic chemistry really a jungle? More in particular, we'll look at bond line drawings. So we will be starting the chemistry course with organic chemistry. Now I'd like to do a little bit of a preamble before we start to look at the page number 3 of your course pack. And the preamble involves introducing you to the father of organic chemistry. So here we have Frederick Weyler, who lived in the 1800s. And in 1828, Weyler synthesized the compound urea. Now, essentially all he did was take a compound that involved silver, a metal, and then NCO. So this is isocyanate. And the idea is that this is an inorganic compound. And by heating this inorganic compound, he formed urea. And you can see the formula and chemical structure for urea, NH2CO, NH2. Now, why this reaction was so remarkable is it involves changing an inorganic compound to an organic compound. Now, in those days, people thought that inorganic compounds belonged to the non-living, to stones, to soil, to earth, whereas organic compounds could only be found in living creatures. So the fact that he was able to do this in the test tube was rather remarkable. Weyler was excited by his discovery. He says here, "I cannot, so to say, hold my chemical water, and must tell you that I can make urea without thereby needing to have kidneys." Now, of course, this reference has to do with the fact that we find urea in urine. And so this particular discovery underthrew the theory of vitalism and set the stage for the discipline of organic chemistry. Vitalism was the thinking that organic compounds could only be found in living creatures. So the fact that we could synthesize an organic compound in the test tube indicated that organic compounds can be in fact synthesized by human beings. There was nothing in particularly special about organic compounds that existed in these living creatures. So the vitamin C that you find in a bottle is no different than the vitamin C that is found naturally in oranges. Now, there may be some benefit in eating oranges that comes from not just the vitamin C, but the vitamin C chemical is indeed the same. Now, only 7 years later, in 1835, Frederick Weyler was reputed to have said, "Organic chemistry nowadays almost drives me mad. To me it appears like a primeval tropical forest, full of the most remarkable things. A dreadful endless jungle into which one does not dare to enter, for there seems to be no way out." So even then he began to appreciate the challenges in working in organic chemistry, the plethora of possibilities for having carbon-carbon chains. So one of the things in this course is I hope that you don't actually feel that organic chemistry is a dreadful endless jungle, but you will appreciate some of its complexity. And I hope to be able to navigate your way through. So one more thing in terms of the preamble. One of the biggest challenges in organic chemistry is to relate structure to function. So for instance, if you look at these 6 different organic compounds, and you'll see that these are structures that all involve rings. They all have CH3 groups on the top of the ring, and then there's some variations. Many of them have OH groups or C double bond O groups, and I've given the common names. Now, the amazing thing is each one of these interacts very differently with our bodies. So for instance, the carvacrol is the main compound in the oregano spice, whereas thymol is the main chemical in the thyme spice. Menthol and menthone are both found in peppermint, whereas carvone is found in spearmint, and carvone negative is found in spearmint, and carvone positive is found in caraway. So you will come to be able to distinguish a little bit better the difference between negative carvone and positive carvone. But one of the amazing things is all of these structures look somewhat similar. And yet it's remarkable that the receptors on our tongue and the receptors in our nose interact differently with these chemicals and give different responses to the brain. As such, it's not really well understood how structure relates particularly to function. And this is important in the pharmaceutical industry, where if you're trying to create a drug which would target a particular enzyme and you want it to only target that enzyme and nothing else, you have to know what is the effect of changing various groups in the structure. And so we're learning more and more about this, but it's still somewhat of a mystery. But let's get to a level where it's easier for us to interact, and I'm going to look at page number 3. And at the top of page number 3, I'm going to ask you to use a little bit of space and consider these 3 different structures. So I ask you to stop the video and write down these 3 structures as quickly as you can. Go now. Okay, so I've hoped that you reproduce these 3 different structures, and I think you probably realize that the structure on the right, this guy right here, was probably the easiest for you to draw. And that's the whole point, is that organic chemists like to use bond line drawings because they're the easiest to use. And so I've made a couple of notes here that it's the same molecule in all 3 cases, but the bond line drawing is the quickest to draw, it's the quickest to read, and it's the best way to communicate. Now, just to help you see how it's the same structure in all 3 cases, if you look at the following structure, you see a CH3 in brackets 2, and that means that both of those CH3s are attached to this carbon right here. All right, and so if you're writing on a keyboard, this is the way that you can write out the structure. But and it can be written out fairly quickly, but it's a little hard to interpret that both of those CH3s are attached to that one carbon. Now attached to that one carbon, we then have a CH double bond CH. And it's important that you understand that those H's are attached to the carbon as such. So you can see it down here. Those H's are attached to carbon. It's not carbon H double bond carbon. Because of course we know H's can only form one bond. And so drawing that condensed structure, it's a little bit hard to interpret. It's easiest to interpret this structure, but of course it takes the longest to write out. However, if we draw a bond line structure and understanding that carbon has to make 4 bonds, we should appreciate that on those particular carbons right here and at the corner, indeed, those are carbons there, those carbons are attached to hydrogens, and as such, therefore, the carbons are making 4 bonds to other things. Just to clarify, if we focus on this guy, this carbon is making a sigma bond here, it's making a sigma bond to the hydrogen, it's making another sigma bond to another hydrogen, and it's making a pi bond. So indeed, it's making 4 bonds. Likewise, let's say we focus on the carbon right here. We know that carbon has to make 4 bonds, and therefore we recognize that indeed what we're not writing in, but understood is there, are the 3 hydrogens. So this is the nature of bond line drawings, and the rest of this lesson is unpacking a little bit how to work with bond line drawings. So moving down then, I'd like to first of all look at drawing bond line drawings for single bonds. So you've got some space to reproduce bond line drawings, and the key here is to ask yourself how many carbons are present. So in the first structure, I count, and maybe I'll just number them here, 1, 2, 3, 4 carbons. So the idea is that you would then draw lines that would represent these 4 carbons, and it would look something like this. The idea is that you draw them zigzag so that you can actually distinguish one carbon from the other. And so if I now number the carbons, I got 1, 2, 3, 4 carbons. Now you can draw this in a variety of ways. So I go or, you could also draw it like this. It would also indicate the fact that there are 4 carbons. So at each of the corners and on the ends are the carbons. So we consider the next structure. The easiest way to do this is to look for the longest continuous chain, and that might be something like this: 1, 2, 3, 4, 5. So I have a 5 carbon chain where I've got a CH3 group coming off of carbon number 2. So therefore I could draw the bond line drawing like this. So once again, I'm going to number my chain: 1, 2, 3, 4, 5, and here is the CH3 group, and I'll circle the CH3 group over there. Now, this can be drawn also in different ways. So for instance, it can be drawn like that, where if I number the chain, we can still see that I have a CH3 group coming off of carbon number 2. You could even draw it backwards if you think. So I could draw it like this. So I got 1, 2, 3, 4, 5. But instead, I'm going to put my CH3 group there. So I would number my carbons like this. 1, 2, 3, 4, 5. It's the same structure. All right. Finally, if we look at this last structure right here, we can see that we've got what looks like a ring, and it's actually rather tedious to write out all the CH2, 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 etc. But if you draw it as a bond line structure, it's this nice hexagon ring. Okay, so we use bond line drawings to represent the single bonds, and this is the fashion that we do this. Let's take a look at how we need to draw double bonds. And so I'm coming now to the right-hand side of the page, in the middle of the page, and we have here a ring, pardon me, we have a chain that has a double bond. I'm going to number my carbons, 1, 2, 3, 4, 5. Okay, so I need a 5 carbon chain, so I'm just going to reproduce that, and note that we do have a CH3 group coming off of carbon number 2, so that'll look something like this. All right, so 1, 2, 3, 4, 5, and coming off of carbon number 2 we have the CH3 group. But what's different is we have this extra line that of course represents the pi bond. Now I'd like to mention something in terms of how we should be drawing these double bonds. And to help you with this, we're going to be reviewing something about geometry. So I'm going to focus on carbon number 5, and as you know, on carbon number 5 we do have indeed 3 hydrogens attached to that. Carbon is going to be making 4 bonds, and 3 of those bonds are going to be to hydrogens. So if I write in the hydrogens, and if I want to, in a sense, show the geometry. Now many times we don't need to show the geometry, but in this case I want to emphasize it. It's important to realize that if carbon's making 4 bonds, its steric number is equal to 4. This means that it's sp3 hybridized. So I'm reviewing some things from last semester. Further, we can say that its electronic equals the molecular geometry, which equals tetrahedral. Okay, and so to emphasize that, I can write in a hydrogen, and then I can write in another hydrogen here to again show the tetrahedral structure. And so a bond coming out at us and a bond going into the plane, and therefore you can see, oh yeah, this carbon is tetrahedral. Again, don't need to draw this unless you're specifically asked to, and you'll see later in the semester when we get to certain sections I'll be saying, yeah, you've got to draw this in 3 dimensions. Let's now focus on carbon number 2. Okay, so I'm focusing on this guy right here, and carbon number 2, I hope you can appreciate, has a steric number equal to 3. Now just to review, steric number is all the sigma bonds plus any lone pairs. So carbon number 2 is making 3 sigma bonds. It is sp2 hybridized. Its electronic equals molecular geometry, which in this case equals trigonal planar. Okay, now what this means therefore is the bond angle about that carbon is actually 120. Now just to make a reference here, let's go back to the tetrahedral. You might remember therefore the bond angle here is 109.5 degrees, whereas the bond angle about this carbon at all the different regions is 120. This is also 120, and etc., right? Now, given that the trigonal planar is a planar structure, it can be actually drawn in 2 dimensions. And so when you're drawing a double bond, you should try to resemble this 120 degrees. So for instance, I can draw a hydrogen in here and still have this 120 degrees. What's not a good idea is to draw your double bonds like this, for instance, where I'm implying a 90-degree angle. Okay, so don't do that. In a similar way, let's look at what happens when we draw a triple bond. Okay, so I'm going to focus on this carbon right here in our structure, including the triple bond, and I hope you can appreciate that the steric number for this carbon is in fact 2. The hybridization is sp hybridized. Its electronic equals the molecular geometry, which is equal to linear. And the bond angle here is 180 degrees. So it might come as a bit of surprise, but it's totally logical that we would draw the bond line drawing like this, where the carbons that I've just circled here are found at the well, not corners, but found at the ends of the so-called triple bond. All right, and so this bond angle is actually 180 degrees. And so I'm going to be encouraging you to draw your triple bonds like this. What's not really appropriate is to draw your triple bond something like that. You know, that's more appropriate for a double bond, but not for a triple bond. Okay, so don't do that. All right, so we've reviewed a little bit about drawing bond line drawings. I'd like you to practice a little bit, and we're first of all going to practice with some simpler examples, and then we'll get to some more complex examples involving numbers of hydrogens. But before we get to that, I realize I have one further structure which is not actually drawn on my page, but is shown on yours, and so I think we should put it in, and it's this benzene structure. So let's just put this in here. Okay. So actually, in me drawing it out, you can see that it's actually rather tedious to be drawing out this particular ring if I have to show all the carbons and hydrogens, especially if you've got the bad handwriting that I do. All right, so I'm going to put the double bonds in. Okay. And so that's more or less what you have drawn. And so this does indeed involve the double bonds and the idea of the 120 angles. And now if we draw this as a bond line structure, it's much easier. So it just looks like this, right? And indeed, you've got the 120 angle. Now recognize that we do have the hydrogens off on the end, and sometimes we'll write them in for emphasis, but we don't have to write them in. We know that they're there. Okay, so now let's get down to be counting carbons and counting hydrogens. Okay, so found in the first exercise, I have represented 8 different structures. And the first thing I'd like you to do is to just interpret the bond line structures in terms of counting the number of carbons. So I encourage you to stop the video and count each of the carbons, and then we'll compare the answers. Okay, so I hope you stopped the video. I hope you've counted all your carbons. So I'm going to put out the number of carbons here. So if you counted your carbons correctly, this is what you should have. Now, one of the structures that students sometimes have trouble interpreting is this one right here, where I'm going to count around. You've got a ring structure, right? 1, 2, 3, 4, 5, 6. And the idea is that there's a bridge that's joining carbons 2 and 5. And so here's our 7th carbon right there. Now that's different than, for instance, the next structure on the right, where I got 1, 2, 3, 4, 5, right? And then what I've got, and then 6, and then down here 7. Okay, so indeed that is 2 rings that are held together, and each of the rings are 4 carbons long, but they share a single carbon, and therefore there are 7 carbons there. All right, so just to distinguish between those two. So the next thing is to make sure that you can count the hydrogens appropriately. So I ask you to turn the page, look at page number 4. And the idea of knowing the number of hydrogens is based on the fact that neutral carbon atoms always have a total of 4 bonds. Now, I emphasize the idea of neutral because you're going to see in a week or two, we'll be dealing with carbons that in fact have a charge. And when they have a charge, something else can happen. But for most of the structures that we'll be looking at in the next week, all the carbons will be neutral. So let's go one step at a time. I'd like you to examine this particular structure, which has the benzene ring and another single bond ring structure. And I'd like you to take note of all the carbons that have 0 hydrogens. And so those will be the carbons that are already making 4 bonds. So maybe stop the video and see if you can find those carbons that are already making 4 bonds. Okay, so if you chose correctly, it would be these guys, right? And just to give you as an example, I'll focus on the one out here. All right, so this carbon, it's making a sigma bond, another sigma bond, another sigma bond. So that's 3 sigma bonds, right? And let's just label sigma bond. And then over here I've got a pi bond. So indeed, that carbon is making 4 bonds. Now let's take a look at the carbons that have 1 hydrogen. And so those will be the carbons that are already making 3 bonds explicitly in the structure. So you may want to pause the video and find those that have 1 hydrogen. Okay, so the ones that have 1 hydrogen are these guys. And I'm hoping that your brain will start to be trained to immediately pick out, oh yeah, these carbons are already making 3 bonds, whether they be a sigma or a pi bond, and therefore they're missing a bond, and that bond is a bond to a hydrogen. Right? Don't need to write in the hydrogen. Sometimes we will, but don't need to. Next, look for the carbon that has carbons or carbon that has 2 bonds. And I hope you picked out this guy. And there's only 1 carbon in this case that has 2 bonds. A common thing is in the middle of a chain or along a ring if there's nothing else attached to that carbon, 2 hydrogens. And finally, the carbon that's making 3 bonds to hydrogens. And one of the things that you'll start to notice is those carbons that are at the end of a chain or sticking off of a ring will be the ones that have 3 hydrogens. So these guys on the end here. Okay, with that little bit of a lesson, let's take a look at the exercise number 3. So count the number of hydrogens, part 2, right here. So these are the same structures that we saw on the previous page where we counted the number of carbons. So now I'd like you to count the number of hydrogens. Please stop the video and go ahead and do this. All right, so if you've counted correctly, these are the number of hydrogens. So this ends for now as far as I'd like to get in terms of the chem activity number 1. There's a little bit more to do, but we'll do this together in class. So hopefully this gets you started in working with bond line drawings.